Hello everyone, in this RLC car tutorial number 52, we are going to talk about the different operating modes of the parallel and series RLC oscillator. But we will start by explaining the energy transfer between L and C, then the starting condition to obtain the oscillation, then the negative resistance with N and S characteristic, and some solution to obtain this negative impedance condition for parallel and series topologies. Until the invention of the coil in 1820, the capacitor must have been boring. But from 1820, the capacitor must have been happy to have an inductor as a new playmate. The LC oscillation principle is based on the exchange of potential energy EC equal CV square over 2 stored in the capacitor and the kinetic energy EL Li square over 2 stored in the inductor. Thus, both the capacitor and the inductor play an energy exchange role. At t equals 0, the capacitor is charged. EC is at the maximum. The switch is in position 1 and the coil has 0 current, EL equals 0. Just after the switch, SW is put in position 2. The inductor has a voltage VL equal to the initial VC. This voltage across L imposes a current slope of VL over L. During the time C is discharged, to obtain 0 volt, the current of the coil increases to the maximum with a slope of 0 because VL equals 0. But now EC equals 0 and EL is at the maximum. All the potential energy of the capacitor that has been transferred into the coil as kinetic energy. As the current in the coil cannot stop, it will continue to discharge the capacitor to obtain a negative voltage to get the same potential energy as the initial one, and so on, until returning to the initial state. Then the switch returns to position 1, the voltage VC will maintain the charge and the inductor will remain at 0 current, forcing VL to 0 volt. This slide is also on the RLC car tutorial number 4 speaking of inductor. So if you are interested, you can visit the playlist Electromagnetism. Of course, in this presentation, we are talking about ideal capacitor and inductor without any losses. So the oscillation amplitude is constant and endless. Mainly because of the parasitic resistance of the coil, but also because of the capacitor plate contact, the LC circuit becomes the RLC circuit. If we look at the sinusoidal current, I, in blue, we see that at each energy transfer, part of the energy is lost, so the oscillator has less and less current. In the end, the current will be 0. This is a damped oscillation. To be able to start, the total resistance of the circuit must be negative. The negative resistance means that energy is supplied to the oscillating circuit. The startup time depends on the selectivity of the resonant circuit. Indeed, only the noise frequency selected by the resonant circuit is amplified. If the circuit has a high selectivity, like a quartz, for example, the startup time can be very long. Then, when the amplitude increases, the saturation of the circuit will force the module of the resistance Kr to decrease to the exact value of R. This saturation will give the final amplitude of the oscillation. As the amplitude increases, the resistance Kr will decrease, and the amplitude will stop increasing when Kr is exactly equal to R to make the total resistance equal to 0 ohm. In those curves, the resistance R is represented by the slope V over I. As the slope is negative, this means that the resistance is negative on both diagrams. But the change appears when the resistance is no longer linear but starts with saturation. On the left, the saturation type is called N characteristic. On the right, the saturation type is called S characteristics. N and S forms have opposite behavior. With N characteristic, when the resistance reaches saturation, the absolute resistance value decreases. But with S characteristic, when the resistance reaches saturation, the absolute resistance value increases. For N characteristic, VDC equals 0 does not work because we will have three different operating points. So the only way is to bias with a 0 DC current to get a single operating point. On the same way, with the S characteristic, only the VDC equals 0 will work to get a single operational point. So the N characteristics fits well to the series RLC because the DC current is 0 due to the series capacitor. Similarly, the S characteristic fits well to the parallel RLC because the coil provides a DC short circuit with VDC equals 0. The serial RLC oscillator must be in series with a negative resistor of characteristic N. This negative resistor can be replaced by a negative impedance converter, INIC minus. The impedance of the inverting input is minus R1 over R2 multiplied by RC. Similarly, a parallel RLC oscillator must be in parallel with a negative impedance of characteristic S. This negative resistor can be replaced by a negative impedance converter INIC plus. The impedance of the non-inverting input is minus R1 over R2 multiplied by RC. Of course, for the series RLC oscillator, there is another solution to create a negative impedance like the tunnel diode. As the diode characteristic shows, it is obvious that we need to bias the diode with a current source I0 to get a single operating point. During saturation, the tunnel diode provides an increasing negative conductance, which means that the resistance will decrease during saturation. This is exactly what we need for a series RLC oscillator. As shown in the schematic, if we connect a forward biased tunnel diode in parallel with a series RLC, of course, because of the series capacitor, the DC bias current I0 will bias the tunnel diode. For the parallel RLC, other negative impedance solution also exists with the transconductance amplifier. The output is shorted to the non-inverting input and the inverting input is grounded, forcing a DC voltage of 0 volt on the parallel RLC oscillator. If we look at the output current I equal to GMV, we will notice that the current is flowing out of the amplifier, which means that the output impedance of the amplifier seen from the outside is negative. The I versus V characteristic shows a current saturation, which allows for an increasing conductance upon saturation. So if we connect a parallel RLC across the transconductance output, the resonance circuit will start oscillating with a low conductance, allowing for an increasing amplitude until saturation, which allows for a lower conductance exactly equal to the RLC conductance. When the negative resistance minus R1 is in the linear region, the resistance is given by the ratio V1 over I1. When the magnitude of the current I2 goes out of the linear region, see the red line, the absolute value of the negative resistance decreases because the magnitude of the voltage is limited due to the saturation. Of course, as the magnitude of V2 is limited and the current I2 continues to increase, the resistance R2 decreases. It will decrease until the absolute value of minus R is equal to the uppercase R. So, The negative resistor with N characteristic fits well to the RLC series circuit because minus R plus capital R must be negative at the beginning to start the oscillation and then be equal to 0. For RLC series, only the negative impedance converter minus, NIC minus, can work because the stability condition is Rg greater than R1 times Rc divided by R2. Due to the series capacitor, the RLC DC impedance is infinite with DC current equal to 0. So the condition Rg greater than R1 times Rc divided by R2 is always valid. So the source voltage with Rg can be replaced by a RLC series circuit. I want to thank you for your attention. On my next RLC tutorial number 53, we will talk more in detail about the negative impedance converter. So see you soon and stay tuned.